I'm Belanie, and I'm going to talk about my report, Applications of Triangular Anycast Forwarding. So in my report, I evaluated the performance of Anycast systems in terms of the quality of paths from clients to the Anycast site that they're routed to. And I found that under 50% of clients were being routed to the optimal Anycast site that provided the best latency, and that on average, the paths chosen were over 50 milliseconds longer than the optimal path. IP Anycast is a network addressing and routing methodology where network operators are able to announce the same IP address prefix from sites in different locations. In this figure, you can see kind of the cloud represents, like, say, the world in different countries, and you can see that these sites all address the same, all advertise the same address, but they're distributed geographically so that the client can be routed to any single one of them. And each of these sites can provide the same service to the end users, and clients' requests are automatically distributed among these sites according to the Border Gateway Protocol. And this kind of goes against the traditional internet protocol, which expects each network interface to have its own unique IP address. IP Anycast instead allows clients to potentially be routed to sites that are closer to them geographically, which will improve latency, and also allows for a service to balance the load of requests among the different sites. Triangular Anycast forwarding is a new mechanism that employs IP Anycast in order to create kind of an intermediate step in between the clients and the services. So instead of having users connect directly with the service they're requesting, the Triangular Anycast forwarding system directs users first to an instance of an Anycast address, and then at that instance, any unwanted traffic is filtered out, and only the real legitimate traffic is passed on to the actual service that the user was requesting, and then that service can then send a response back to the client. So you can see in this diagram here that kind of triangular format where, again, these sites are distributed geographically and the client will be routed to one of those sites. Then that site will forward the traffic onto a service and the service will go back to the client. So triangular Anycast forwarding is currently being employed by Akamai for two main purposes. So the first is to protect web-based services from attacks with their Prolexic routed product, where the Anycast instance will drop any abnormal traffic or attacks and then forward on only the legitimate traffic to the requested service. The second is to aid in self-service billing through the Brave system, which helps track which user requests can be ignored when billing. So a cellular data operator can make an agreement with a content provider where customers won't be charged for any bandwidth they use when requesting content from that provider. So the client would be routed to an Anycast address when they get a link to download from that specific content provider, and any charges for accessing this content through that site will be dropped. So my study is part of a larger study that proposes this Hecatoncheires system, which is the first Anycast planning system that aims to optimize the performance of network applications by enabling the most feasible and optimal sites among the available sites to advertise the Anycast prefix. So a lot of previous studies of IP Anycast have found that good behavior of the system is based upon careful creation. So a system that's deployed in an ad hoc manner won't necessarily provide good latency, fast failover, or effective load balancing. So that means basically that the clients might not be routed to the closest or best site. Clients may not be routed to another site quickly if one of the sites becomes unreachable, and that some sites might receive disproportionately more traffic than others. So Hecatoncheires uses a performance optimization problem to provide kind of an optimal subset of sites that the Anycast network has available. And this subset will achieve better amortized performance and also balance load better. So ultimately, this system can help reduce average round trip time by 45% compared to kind of the worst setting of the network. So now I'm going to go into my experiment. So I set up my experiment using RIPE Atlas, which is a network of probes all over the world that provide information about internet connectivity and reachability. There are thousands of probes in the network, and users can host probes or create custom measurements from those probes to specified addresses. So the way that I set up my experiment is I chose 3,000 probes, and I chose roughly one probe per autonomous system in the RIPE network. So an autonomous system is a collection of IP address prefixes that are kind of all connected and all under the control of one administrative entity that decides upon, certain policies for that group. So choosing one probe per autonomous system allowed for a variety of routing policies and also potentially some geographic variety for the chosen probes. And then I set up 7 different sets of measurements using these probes. So the first 6 sets of measurements were pings from the 3,000 probes to the 6 unicast addresses that represented the 6 possible Anycast sites for this Anycast, or the 6 possible sites for this Anycast system. And then the 7th set of measurements were pings from the 3,000 probes to an Anycast address, where kind of those pings could be routed to any one of those sites that I looked at for the unicast addresses before. And then kind of some of the limitations for my experiment were that not all 3,000 probes responded and pinged each of those sites. So that kind of reduced by about 100 the number of probes that we could use. And then also only about 1,800 probes could be captured and associated to their catchments. So in this kind of last measurement set where I pinged the Anycast address, we used Wireshark to capture the packets from these probes in order to match the probes to the site that they went to. So the catchments were kind of the set of probes routed to a certain Anycast site. So now I'll go into some of the results from this experiment. So the first is path chosen. So I found that 45.23% of the probes were routed to the best site, but there's still significant amounts of probes, like over 50% of them, that went to a suboptimal path. So a little bit over 26% of them went to the second best path, and about 10.5% of the probes went to the 5th best path. So this kind of shows that there's a lot to be improved in terms of routing clients to their optimal site. Additionally, I looked at the route time. So I found that the average round trip time difference between the chosen path and the best path was about 54.51 milliseconds, and the maximum difference got up to over 500 milliseconds. It's also interesting to see that there was a significant amount of probes that were kind of in the 200 to 300 second difference area on this chart. But yeah, this also shows that there is a lot to be gained in terms of improving the amount of time it takes to get to the different sites. Lastly, I looked at site popularity. So I saw that GRE2 and GRE7 were sent a lot more traffic than others, which could indicate rank order. So clients have a somewhat linear preference order of which Anycast site their traffic will be routed to. So you can see that GRE2 and GRE7 were probably at the top of this preference list for a lot of the probes, and it could be significant to see how kind of Anycast networks should be structured. So kind of some discussion based on these results. So the results that I found are significant because they indicate the need for a system like Hecatoncheires, which kind of aims to reduce round trip and one-way time in Anycast networks by enabling the optimal sites among the available sites to advertise the Anycast address. We see that in a non-optimized system, only about half of the paths chosen to the Anycast advertisements were the best path, and the average path is over 50 milliseconds longer than the best path. So there's a lot to be gained in traditional Anycast systems in terms of round trip time, and also in triangular systems, because that one-way time to the Anycast instance can be improved, thereby improving the whole triangular time. Additionally, the analysis that was done on the results above can be reused to help determine latencies based on which Anycast sites are being advertised together. So the catchments can be found for different configurations of these 6 routers, and analysis can be done on those sets of routers in order to determine which configurations provide a higher percentage of probes being routed to the Anycast site that provides them with the best latency. Also, analysis on the different configurations of the 6 routers can help identify the rank orders. So end users create these priority lists and send their traffic to the highest ranked site, like I mentioned before. So being able to identify which sites receive more traffic and therefore maybe at the top of these lists can help with load balancing and also the selection of optimal sites. So Hecatoncheires can use this information as an input in order to decide which Anycast instances should be advertised. And this can minimize latencies and encourage the optimal instance to be at the top of the rank order list for a client.